Whew, here we go. Okay. Definite integral and Riemann sums. We are going to take the definite integral and we are going to express it as a limit of Riemann sums, which I'll write for you in just a second. But first, let us consider the curve f of x is equal to x squared and how we would evaluate that sum using right-hand sum for rectangles from 0 to 2. So if I create a drawing here and I have a curve, I have x squared from 0 to 2. Okay? Who can tell me how would I write that sum? We want to take the width times the sum of the heights. What's the width? Not 2, but 2 is the width of the interval, but the width of each rectangle is? Try again. There's 4 rectangles. A half. What you did is you took 2, okay, minus 0, and you divide it by the number of rectangles to get the width. Okay? Then, what is the first spot that we evaluate our height? What is the beginning spot for this? Yep, we're going to start at 1/2. If you look at the interval, we're going to divide up into 4 spots. That's 1, that's 1/2, that's 3 halves. And you're going to do the right side of each interval. So very good. So we have 1/2. And what will we do to that 1/2? Okay, what do we do to the 1/2? Square it. Why? So that's how we determine our height, by plugging in the function. Very good. What's our next number we plug in? 1. Then? And the last number? Very good. So you can see here that that's how we generate the sum using 4 rectangles on the right-hand side. Now, that's what we practiced last week Friday. You had a worksheet on that. You should have been able to do that for all your problems, right? We divide it up into 4 rectangles. We're going to use that graph as a picture for a general function in a little bit. But no, that is not the graph of x squared. Okay? All right, so, okay. Now here's where you really got to start thinking. You just calculated the width. The width was 1/2. Suppose I want to know the width of n rectangles and not 4 rectangles. What would the width be of n rectangles? Very good. So what Kyle sees is that if we want to find width, we take our interval, we subtract it, and we divide by n. So being it was from 0 to 2, took 2 minus 0 and divided by n. That's how we got our width. We got that? So that's an important piece we needed. The second piece we needed is we needed the spots at which we evaluate our heights. We needed the spot at which we evaluate our heights. Well, let's think about how we came up with these numbers. How did you come up with 1/2? How do we decide that 1/2 was the first one? Okay, halfway between 0 and 1, so we know it's divided. Why didn't you select 0? Okay, so that would be the left-hand sum, okay? So would it be fair to say that if you took your starting point, so right here, starting point A, if you went over 1 width, that would be where we started? Everybody agree? So as you look at this picture here, this gives us a representation. If this is our function, f of x, this is not x squared. This is just a general function, if you understand the idea. I'm going to start at A, then I'm going to move over 1 width. And that's where I create my first rectangle, right? So for this problem, what is our starting point for our interval? Starting point for our interval is 0. And if we go over 1 width, that brings us to a half. Our second spot where we evaluate the height, instead of going over 1 width, we're going to go over 2 widths. And that will bring us to our second rectangle. So if we went over 2 widths, that brought us to 1. And then we'll go over 3 widths, right? So if you want to know the x values for which we evaluate the sum, we start at the beginning point of our interval, which is a, and then we add on widths. How many widths? Well, we start with 1, and then 2, and then 3, and we go all the way up to infinity. To represent that we have 1, 2, 3, 4, 5, so on and so forth, we're going to use the number I, the letter I. Okay? So let's calculate this formula right here. It says for what x values do we evaluate the sum? What is a? What's the beginning point of our interval? 0. Plus, what's b minus a over n? 2 over n. We multiply by I. That expression simplifies to 2I over n. This thing, because you're gonna that's your formula. Yeah. We're gonna use that over and over again. You're gonna use this just like you're gonna use that for every problem. This is my width. This is all of these things right there. So I'm going to write on the board now how we express the definite integral as a limit of Riemann sums. All right, just wrote a bunch of stuff on the board for you guys. We'll write it on YouTube later on. We did it in order to express the area as a definite integral and as a limit of Riemann sums. So we have the integral. Bounded from, where's the beginning? For this problem. 0 to what? 2. So that means, what is the area from 0 to 2 underneath the curve? What's the curve? X squared, and we attach a dx. Is equal to the limit as n goes to infinity of the sum from I equals 1 to n. It always starts like that. Don't be confused with where I got any of those pieces. Okay, what is x sub I? At what points do we evaluate the heights? What's the expression up here that tells me where we evaluate the heights? 2I over n. That's my x sub I. What do I do with that? You plug it in. So if I plug that into my function, I will square it. Times delta x. What is the width of each rectangle? 2 over n. You're going to see what happens here. It's beautiful, okay? What we've done is we are going to, guys, this is what we've done every single time. We have the width times the sum of the heights. Width times the sum of the heights. And instead of doing 8 of them, we're going to do an infinite number. Let's do it. We got the limit as n goes to infinity of the sum from I equals 1 to n. And now, instead of writing 2I squared over n, I'm going to actually square that out. What do you get? 4i squared over n squared times 2 over n. Everybody okay with that step? Equals limit as n goes to infinity of the sum I equals 1 to n of, we multiply that, combine some terms, what do you get? 8i squared over n cubed. Does it bother anybody else that I have two variables here? I have I and I have n. Which do you think is the variable we want to be left with? N, because we're going to allow it to go to infinity. I have to get rid of I. Oh, super great for me because I have it sitting right here. Look at this sum that we wrote down earlier that we got from our mathematical induction work. We could get rid of this sum from I equals 1 to n of I squared by substituting that piece in. So I'm going to write this as the limit as n goes to infinity. I'm going to pull out the 8 over n cubed in front. So I have the sum of I squared left. What can I replace sum of I squared with? I should write from I equals 1 to n, my bet. Yeah, I can move it right in front of the sum piece. Yep. It's a multiplier. Yep, it's the third thing down. It's this guy right there. N times 2n plus 1 times n plus 1 all over 6. That's my substitution. Now instead of having two variables, I have one. And now we just have an expression that involves an infinite limit. We have 8 over n cubed times n times 2n plus 1 times n plus 1 all over 6. Do we know how to do infinite limits as part of your first or second quarter final exam? This is a piece of cake upside down. We've seen this before. So let's just multiply it out. Limit as n goes to infinity of, okay, so I have to FOIL here. So 2n times n is 2n squared times n times 8. What will that give me? 16n cubed, yep. And I have 2n times 1, and 1 times n is going to give me 3n times n times 8, 24n squared. I have 1 times 1 is 1 times n is n times 8, 8n. What do you have in the denominator? 6n cubed. Do you remember how we handled these infinite limits? What did we do? Factor out the n cubed. Good. I'm left with 16. It's 24 over n. 8 over n squared. All over 6n cubed. As this goes to infinity, what's going to happen to the 8 over n squared? It goes to 0. And 24 over n goes to 0. And n to the thirds cancel, and you're left with, which is, whoops, sorry, 16 over 6, which is over 3, which is 2.6 repeating. That is the exact answer, not an approximation. Take out your calculator. Go into your calculator and type in x squared. Go second calculate. What do you think I'm going to press? 7. What is my lower bound? 0. Upper? 2. No approximation, folks. Exact. This is an approximation. That's what your calculator can do. We had the exact value, 8/3. We added up the area of an infinite number of rectangles. In order to do so, we had to use some Riemann sums. We had to write some interesting equations down, but this is where we're headed. Tomorrow, what we will do is instead of using an x squared, you can see that we are going to use x to the third. So instead of using this formula, which one would I use? The last one. Your assignment is to take a scratch sheet of paper and to try to do this one. It follows almost identical to the first one. And then at the beginning of class tomorrow, we're gonna go through it together and see if you came up with the real thing. Okay? Yep, try it on scratch because we're gonna fill this out tomorrow in class, and you want to see if you can do it. This is just to try to keep up with what we're doing, so you can see what's going on. Okay? Then look at what's gonna change. The next kind of problem, instead of just having one term, we have two terms. And then with the next problem, we have three terms, and we don't start at 0. We start at 2. So these get significantly more challenging. So if you could try to follow what we did and just do the next problem and try to work your best through it, and at least figure out, if you don't know how to do it, figure out where your questions are, and then we're going to be, trust me, tomorrow will be a lot easier. So that's all I want you to do. Work on that one problem, and we'll cover it tomorrow, okay?